user-defined body tapping recognition with offline learned probabilistic representation. So this work was done while I interned with Xiang Li at Google Research. So in 2015, Apple reported that average users have 119 apps, all of which they have to navigate only through a very tiny window on their smartphones. So this work is the third piece of the trial of body-centric interaction, in which the idea is to use the user's body to extend in the space for interactions, and which is also explored in a couple of previous works. However, when it comes to the implementation, this concept kind of fell short because there are several implementation issues. Firstly, most of these previous work remains as proof of concept prototypes, and often when there is feasible solutions, there's always too many constraints on the users performing the gestures. So our research goal is very clear. We want to enable body tapping gestures to solve the information overloading problem, but we want to provide feasible solutions with as few constraints as possible. So by feasible solutions, we want to use just the motion sensors on commodity phones. And by few constraints, we want to gather as few data points from the users as possible as they tap on the body. We want them to tap anywhere they want, and they want them to tap in their own natural ways. So this is very challenging because we want to enable tapping anywhere on the body in unconstrained manners. So what's the current approach? Well, we can follow an offline approach in which you try to gather as much data as possible, and then you train the machine learning model, and then you try to approximate how a user would actually want to tap on the body. However, in this approach, it's only approximation. Because our body is a continuous space, no matter how many points you sample, you can't really exactly approximate how users would select which points on their bodies they want to tap. And besides, it's also difficult to address the physical differences between different users' bodies. So alternatively, you can follow an online approach, on-the-fly approach, in which you do everything on the fly. You let the users say, I want to tap here, here, and here, and then we collect data, and then we do the training and recognitions all on the fly. But the difficulty in this method is it's really difficult to motivate people to provide sufficient amount of training data in order to obtain good recognition rate. So our approach is a hybrid. We combine online and offline. We want users to define where they want to tap on their body. However, the recognition is informed by offline pre-learned models. So here's the pipeline of a system of our approach. So first, we get a number of users, asking them to tap at their body with predefined locations. So we provide a set of locations, asking these users to tap on the body. And then when it comes to an online actual usage scenario, a user would define, say, I want to tap at these 5 locations, and then we also ask them to provide a few data points at each location, which we call templates. So when you run these templates through the offline learned model, what we obtained is probabilistic distributions that describe how likely a user-defined location belongs to a predefined location. Okay? So now users have defined several locations they want to tap, and they start tapping. So we have some unknown tapping data, which we call Y, and the goal is to figure out, in this case, which of the 5 locations the user define is this Y. And remember, we already have the probabilistic representations of these templates on the user-defined locations, and we simply do the same with this data point Y, and then we compute the KL divergence between them, which is, can be thought of as a distance metric between probabilistic distributions, and then we simplify the closest match. So we conducted an experiment to verify our approach. We recruited participants with different ages, heights, weights, and handiness. So before we can actually verify this approach, there's a tiny technical question, which is how you can register a tap, how you know a tap happens. So it's very difficult to use motion sensors because there's a lot of noise. So instead, we use a very simple technique in which we instructed the users to tap the body using the top front part of the phone, which has a proximity sensor, which is usually used to detect when the user receives a phone call. So we found that this serves a very distinctive way to pick up a tap with very few false positives. So in the first part of our study, we collected user-defined body tapping data to simulate the online scenario. To simulate it's actually an online scenario. That's a typo, sorry. So we provide a figure of the body, and then the users select 5 points they want to tap on their body. So it's a mirror image as instructions for themselves. So we have several conditions ranging from different postures to different initial device placements. And the goal is to add variations to simply tapping the body. And the second part of the study, which again is the opposite, it simulates offline scenario. We provide a set of predefined locations, and users again simply follow these predefined locations to tap on the body. But now we intentionally reduced the number of conditions in order to test the robustness of our method. So we analyze our data. So for each user's data, we use that user's data to train our offline model. And then we use the rest as online data. So for each user's defined locations, we randomly sample templates. And notice that these templates might contain data points coming from different conditions. And then we use the rest as the test set. So we then input the offline model, the templates from user-defined locations, and the rest of the data as test set, all into this pipeline. And we repeat this process through all the users and aggregate results. So we compare our method with 2 baselines, an on-the-fly SVM and using the $3 gesture recognizers. So even though overall these numbers are not very high, because we use an unmodified commodity sensors, if we have Gerard's crazy 4,000 hertz sensors, we should expect all these numbers to go up. But it's important to see that our approach outperforms the baselines, especially when there are very few data points. We also observed that even though we have predefined coverage when it comes to the predefined locations, users actually select some unexpected locations that we didn't foresee when we do the offline collection. We also observed that there are inherent confusions between different body parts, such as the shoulders versus collarbones. And finally, observed there are differences between users' choices of tapping locations and their performance accordingly. So to summarize, we describe a method that enables user-defined body tapping empowered by offline learned probabilistic representations. And the general takeaway is, so with inherently related gestures, we can always develop a probabilistic representations from one set of these gestures, which can serve as features to characterize another set. So we hope we can learn from these very specific experiment and maybe explore this method further. With that, I'll conclude my talk, and I'm happy to take questions.
Okay, so we have time for some questions. So could I ask you to speculate? I mean, you mentioned this use of another sensor. What particular problem would this address? I mean, how would you actually, what particular part of your pipeline would actually be addressed by having a higher sensing speed, basically, on some sort of wearable sensor?
I think the pipeline is, when we conducted this project, we expect to be independent of the sensors. Of course, with better sensors or higher sampling rate or better features, you can always expect the number to go up. But I think the benefit of this method is the independence. So we expect it to work with a range of different situations, from fail or poor features to very high-end, high-performance features.
Okay. So, any more questions from the audience? No? Okay. All right. So we'll wrap up the session now. We begin the next sessions at 11:20.